So the theme is going to be titration analysis. I'm going to do two examples. The first one is as simple as you would see on an assessment. The second example would be as complex as you'd see on an assessment. So you're going to see the two extremes. So to determine the concentration of hydrochloric acid, we got our question right away. Now we're told the sample size of hydrochloric acid, and it was titrated with sodium hydroxide, and we're given the volume and concentration of sodium hydroxide. In titration analysis, you have to know both volumes, and you have to know one of the concentrations. Now, you may not be given the equation on a test. You should be able to take HCl and sodium hydroxide and do the neutralization or the double replacement. You can think of it either way. So I have the equation out for you, and we have this 1-to-1 ratio. Now, if you realize this is a 1-to-1 ratio, you might skip what I'm about to do. I'm going to organize this in an ice table, but it isn't necessary. But if you're unsure what to do, an equation in an ice table is a wonderful way to attack all stoichiometric questions. So I'm going to do a little bit of a summary. With titrations, I always like to do a summary. Hydrochloric acid, we don't know the concentration, and the volume is 10.00 mils. So we can't start with HCl because we don't know the C and the V. Our sodium hydroxide, we know the concentration, 1 mole per liter to 4 sig figs, and we know the volume, 14.25 mils. Now I call this a more straightforward question. That 14 mils is the V final minus the V initial, and the math was all done for you. So it's a titration, and you're not given those numbers. So we have two reactants. When you have two reactants and you're doing how much of the other you must have, or the concentration of the other from the first, this is when there's no limiting reagent. They're both running out. And we can figure out the moles of sodium hydroxide, the red, and we can use that to figure out the blue. Because it's a 1-to-1 ratio, that's why some of you might skip the ice table. Okay? You might realize that 1-to-1 ratio and just put out in a line. So my moles is C times V. This is the initial moles. I converted my milliliters to liters. So that red moles, I'm not going to put my units in my ice table. I'm just going to write them next to them for the sake of space. So that tells us how many moles were used up. We assume we went to the equivalence point. All of those were used up. And because of our 1-to-1 ratio, that is also the moles that we must have had of the unknown acid. That amount must have went away, the exact same amount because of the 1-to-1 ratio. So that's the amount we must have started with. And all those identical 0, 1, 4, 2, 5 moles per liter is why some of you might skip the ice table and just realize the relationship. So we're almost done. We know the volume of HCl. We now know the moles. We have everything we need to get concentration of HCl. Concentration is moles per volume. Volume, I'm going to do amount concentration. That's what chemists use, not percent, not ppm or ppb, not moles per mil. So there was 10 mils in the sample. So we'll convert that to liter and keep all those expensive digits from a pipette. And I get 1.425 moles per liter. So a very acidic hydrochloric acid solution. That pH would be negative. It's so acidic that I, or no grade 11 chem teacher would probably give that to you. We might dilute that 10 times, then give you the 10-time diluted solution, which would be 0.14. If it was 10 times less, you could analyze that more safely and just multiply by the 10 times at the end to undo that dilution. So that was kind of a more straightforward question. Would hope most Chem 20s would get that right. This would be, it looks more complex. It's not complex because it's longer, but we're going to have a dilution done. So we have a sample that was diluted, and then there wasn't just one trial done, there's 4. So we have to analyze all 4 trials. So we have a primary standard. So this just goes back to some previous lessons. Primary means you made it up from a solid yourself. So a primary standard of sodium carbonate with a given concentration was made. 10 mils of this primary standard were taken and titrated with hydrochloric acid. So this example is the flip of the intro video or intro we did where the base was on top. We have a base sample, we're adding hydrochloric acid to it. So I would first grab your chemicals, build your balanced equation so you can kind of organize all the data around that equation. So hydrochloric acid reacting with sodium carbonate. My brain likes to put the acid first and the base second. There's no convention on when you write an equation whether it has to be sample first or sample second. It doesn't matter. So in this case, we have our sample as the base and our titrant is the acid. I'm going to reread the numbers and fill in my C's and B's above the appropriate chemical. So I'm going to use green for my acid. Now we kind of have to go up a little bit. Determine the concentration of HCl. So that's what we don't know. So concentration of the HCl is an unknown. So we must be given the volume somewhere. We need it. 10 mil samples, the primary standard. Well, that's the base. The acid, which is the titrant, is actually coming from all of this data. So let's deal with that right away, and then we'll move on to the base. We want the volume of acid, and we're actually going to use the average volume. Our goal is to get the average. We're going to look at all our data. There were 4 trials done. The table has summarized the final volumes. It's done the initial minus the final for you. We got a little above 13, way below 13, way below 13, way below 13. We've got this one first trial that is higher than all the rest. Your guideline is to use a plus or minus 0.2 mils in this course. If you're more than 0.2 mils off the next closest, there was some systematic error there. Maybe you added way too much, something went wrong. So is that more than 0.2 mils from the next closest, which would be 12.8? And yes, it is. That trial is too far away from the other trials. If you think from an indicator perspective with methyl red, so methyl red changes 4.86, and its colors are red to yellow, red to yellow, and then the middle would be orange. We have a base sample, and we're adding an acid, so we're going to start with a high pH and drop down. So we're actually going through the colors in that order. So ideally, with this titration, you would start yellow and stop at orange. But this first titration went flying through the orange into the red. So we see too high a volume, which matches a color that's too far. So if you were writing up this lab, you've got both a volume and a color to say why you're going to exclude trial number 1. So we're just going to add up the other trials. Now, I didn't have enough room to put my units in, which is bad. Those are the 3 volumes, and then I would divide it by the number of trials that I added up. And that comes to a little under 12.8 when you add them up. You keep the tenths. Don't round to the very end, but I rounded it for the sake of the board. So all of that data ultimately gets processed, trials potentially eliminated, though you don't have to, and we ended up with a 12.8 mils. It's a lot nicer when the question gives you that volume, but you can figure it out. So we don't know the hydrochloric acid. The 3 good trials averaged to 12.8. We can move on to our base now. Our sodium carbonate is 0.15 mole per liter, and 10 mil samples of that was used. So concentration and volume. Normally, we don't average all our data together. We normally process each experiment separate. But when we use pipettes, we have this exact same control over one of our reactants. This is the one case where we do averages. So I have everything I need down below summarized. I don't really need to scroll up again. I'm going to start with moles of sodium carbonate. I know it runs out, but the moles is going to be C times V. Then, for the sake of space, I'm not putting my units next to every number. All of that went away. The methyl orange, when the methyl red turned orange. My stoic isn't 1-to-1 this time. If I take the given and look at the required, there's 2 hydrochloric acid for every 1 sodium carbonate. So the required is a 2, the given is a 1. So we have a doubling of the amount of moles of HCl that must have been there. We're assuming all that acid went away, so we now know the amount of the moles of acid. You could skip the ice table and just do that stoic again in a mole ratio calculation. Now we're almost done. We've got our HCl. This is the diluted one. It's not the 10 times stronger from the beginning. We can get the concentration. We know the moles. We know the volume. Highlight, where's the moles? There's the moles. And there's our volume. It's our average volume. We want to do moles per liter, amount concentration, so convert to 12 milliliters. I get a little over 0.2 moles per liter. So this is a pH slightly under 1. Still pretty acidic, but better than the 10 times stronger. So this was the diluted. Way at the beginning, we have that our sample was diluted 10 times. So that original hydrochloric acid is just 10 times stronger. There's no formula with C's and B's or anything. We're just putting back that 10 times. Now you learned about dilutions. If you took 10 mils of the original solution, pipetted it into 100 mil volumetric flask, 10 in 100 would give you that 10 times dilution. And that's it. So this would be super long, as complicated as you get, but it's still the same process. Write a balanced chemical equation, organize your C's and your B's, solve for the C and the D that you know first, and you can work your way to the end one. So we're getting near the end of this unit. The only topic left to come is pH curves, and understand a little deeper about those indicator color changes in titrations.